Hey everyone, my name is Adam Dixon. Welcome to my YouTube channel. Today we're going to be discussing Universal Approximation Theorem. Like usual, there's going to be some woodworking in the background. So what is the Universal Approximation Theorem? Well, the Universal Approximation Theorem states that a feed-forward neural network with a single hidden layer containing a finite number of neurons can approximate any continuous function within a subset of inputs to any degree of accuracy. However, this requires that the activation function is non-constant, bounded, and continuous. Now that's a lot of jargon and kind of complicated. So in simple terms, this means that by using discrete elements like neurons, we can approximate continuous functions, just as numerical integration approximates curves within a rectangle or a trapezoid. Let's explore this with an example. So as you can see, we have here is a ReLU function. ReLU function is fairly simple, and it has revolutionized how we compute in machine learning. ReLU function, or rectified linear unit, basically outputs x if x is greater than 0 and 0 otherwise. It's again simple, yet very versatile. By shifting the scale, for the ReLU functions, we can construct various piecewise linear components. Let's say, for example, the one I did here for ReLU x minus 1. It shifts the function 1 unit to the right, while the next one, ReLU plus 1, shifts the slope to the left. Then you can move on to 2 times ReLU plus 1, and you'll get double slopes, the double slope, and it shifts to the left. And then, as I put in here, a negative ReLU will shift the slope downwards, but keep it in the same direction. And finally, we have the function where ReLU, let's triple it, and negative ReLU times 3, and we'll do it plus 2, x plus 2. And that shifts it greatly to the left, and makes it so as the slope is pointed downwards as well. All right, so now let's explore an example. So we have our ReLU function here, and I think we're going to do y, or f of x, is equal to x cubed minus 3 x squared plus 2x plus 5. All right, so it's a cubic equation, and our goal here is to approximate this function using a neural network. See, so we're going to try and divide the curve into straight line segments. The more segments we use, the closer we're going to get to the approximation. But we can represent these lines by, of course, using ReLU, right? So let's start with our first one here. First one is negative. So our first equation is the final equation. So x equals negative function 1 x, and then function 1 will define as negative 20. Oops, let me change that. It's negative. It's not the first function isn't negative. It's negative 20r ReLU times negative 20 ReLU negative x minus 1. And then let me see here. Let me change the look of it. So it looks a little bit funny here. Almost. There we go. That's a little bit better. And let's change that to +5. Sorry about that. So, our final, let's see. Our second function will be plus function 2 x, and then let's start with function 2. So function 2 equals, so we have the first one being kind of a diagonal downwards, right? And then the second function we kind of want to go slightly less diagonal. So let's do a positive 5r x plus 1. And let's just get the final showing. So it kind of shows that we have a starting point and ending point like ReLU, so the 0 and then the max for the actual value itself. Okay, then let's move on to function 3 here. Plus function 3 by the way, if you guys are interested, for the wood I'm trying to plane the edges so that it's flush with each other, so I'm making a table. But anyways, the function 3 here is going to be a negative 5 ReLU, and that will get us the straight coming along from the end point of the last point here. There you go. As you can see, we got a straight line. I'm kind of looking for. And then, so what do you guys think would be next? Kind of write it down, talk amongst yourselves. What do you think the next step would be? If we continue down the same path, you'd be right. You do the function 4 here. Now let's see. We want to make it go kind of upwards, up diagonal. So let's do a positive ReLU, 5 positive 5 ReLU, x minus 2 for the slope. Let's check it out again. Okay, we have another function here, and it's going to be the fifth function. It's going to be function 5 equals, it's going to be a little bit larger, so it's going to be similar to our first function, the negative 20r. It's going to be positive 15 ReLU, x minus 3. Going to give us a kind of a harsher slope to our lines. And I think you've been noticing that approximation is only really valid within the defined unit range. So beyond x minus 2 to x equals 4, x equals negative 2 to x equals 4, this approximation is only valid within the defined input range. Beyond x equals negative 2 to x equals 4, the network diverges from the original function. To handle larger ranges, we need to input more neurons or add additional hidden layers. Activation functions like ReLU are critical. Without them, a neural network would only produce linear combinations of inputs, incapable of modeling nonlinear functions. The Universal Approximation Theorem shows why neural networks are such powerful tools. By combining simple activation functions like ReLU, they can approximate complex continuous functions within a range. Thanks for watching. Check out my channel for more educational videos. Have a great day.